Development of tool coating. Qiang 1 asterisk, Shiyong Zhang 1, Li Zhuang 1, Jifu Zhang 1, Yaqian Zhang 1 Tianjin Key Laboratory of High-Speed Cutting and Precision Manufacturing, Tianjin University of Technology and Education Tianjin, China. Abstract, with the continuous development of society and the continuous progress of science and technology, people put forward more and more requirements for processing quality and material types. The cutting environment of cutting tools is becoming increasingly harsh, and the traditional coated cutting tools are more and more difficult to meet the needs of people. In order to keep pace with the times, researchers have been exploring continuously to improve the coating structure by doping a variety of functional alloy elements, so as to prepare high hardness, super wear resistant, high wear resistant, high performance coatings, self-lubricating and high temperature oxidation resistant tool coating. This paper focuses on the improvement of coatings in recent years. 1. Introduction as a kind of material surface modification technology. Coating technology can effectively solve the contradiction between high hardness, wear resistance, high bending strength and impact toughness of cutting tools. Based on the above, compared with uncoated tools, coated tools can allow higher cutting speed and improve cutting efficiency. The friction coefficient between coating materials and processing materials is small. Moreover, it can effectively isolate the tool matrix from the workpiece material, and the tool integrity is high, which can effectively reduce the cutting force of the tool and improve the service life of the tool. Traditional transition metal nitride coatings, such as tin, CRN, have been widely used since their research and development. With the rapid development of today's industry, the demand for high-strength and high-hardness materials such as titanium alloy, cemented carbide and high-speed steel is gradually increasing. In order to improve the traditional coating tools, it is difficult to meet the process requirements of high-speed cutting and dry cutting. In order to meet the needs of social development and improve the machining efficiency of cutting tools, the internal structure of the coating is gradually complex. New coatings with high thermal stability, chemical stability, and oxidation resistance at high temperature have become an important direction of coating development. 2. Development of tool coating. 2.1 Binary coating. As the first industrial coating material, tin has mature preparation technology and good metal and non-metallic properties, which has been widely promoted in the field of cutting processing. In addition, due to its unique appearance color, tin coating has been widely concerned in the material decoration industry. The thermal expansion coefficient of tin coating and steel is similar, so it can effectively adhere to the steel one, and the chemical stability of tin coating itself is high, and it is not easy to react with processing materials. The oxidation temperature of tin coating is 550-600. 1 to 3 The TO2 produced by cutting on the prop surface can play a lubricating role, reduce the cutting force and reduce the cutting temperature. As a typical representative of transition metal nitride coating, CRN has high hardness, good wear resistance and the adhesion strength between coating and substrate, which greatly improves tool life and machining efficiency. It is widely used in tool cutting and various mechanical parts, 0.19 to 0.20. Compared with tin, CRN coating has a slightly lower hardness, but its friction coefficient is lower. CR203 protective film is formed on the surface of coated tool during cutting. The oxidation temperature can reach 700. And the oxidation resistance and corrosion resistance of the internal coating are better than that of tin coating. 4. The CR metal coating with high brittleness, poor wear resistance and carcinogenic is replaced in industrial application. 5. 2.2 Ternary coating. With the continuous improvement of cutting speed and harsh working environment, the traditional binary coating tool has been more and more difficult to meet the industrial progress. It is found that doping Al into CRN, tin, and other coatings can effectively improve the mechanical and tribological properties of the coating, and further improve the oxidation resistance of the coating at high temperature. TILN coating has been widely used in dry cutting, high-speed cutting and NC machining due to its high thermal hardness, thermal fatigue, and high temperature oxidation resistance. 6. Al element doping in the coating can replace part of TI, which can strengthen the solution, cause lattice distortion, increase dislocation, and effectively improve the hardness of the coating. The working temperature of TILN coated tools can be as high as 1470, which is due to the fact that Al element is easy to react with O to form stable Al2O3 film, which can act as a chemical and thermal barrier and effectively protect the internal coating from further oxidation. The density and high temperature oxidation resistance of TILN coating can be effectively improved by increasing the content of Al in TILN coating. 7. IJERT 9 IS 090477 www.ijert.org. Published by International Journal of Engineering Research and Technology, IJERT. www.ijert.org. ISSN 2278-0181. Volume 9 Issue 09, September 2020. The internal structure of Al-CRN coating changes gradually with the change of the atomic content ratio of Al and Cr, and with the increase of Cr content, the coating gradually changes from cubic structure to hexagonal structure. Under high temperature cutting conditions, Cr2O3 is formed on the coating surface. When the cutting temperature rises to 900, the coating can still maintain high hardness, the adhesion strength between film and substrate, and wear resistance 8. Balzer's company prepared and launched the ultra-thin and high hardness Al-CRN coating. When the temperature was 1000, the hardness of the coating was still as high as 27 GPa, with high red hardness. Compared with TICN and TILN, the cutting life of the coating was significantly improved. 9. 2.3 Nanocomposite coating. The nanocomposite coatings of MeSIN and MeBN were prepared by doping Si, B, and other elements into the metal nitride, Men, coating. The microstructure of the coating was composed of fine nanocrystalline Men/MeBX contained in amorphous SiNy/Bn. The existence of amorphous SiNy/Bn effectively inhibited the growth of coating grains. 10. Compared with the polycrystalline coating with the same composition, the nanocomposite coating shows better mechanical and tribological properties, which is due to the fine grain size and high hardness in the coating, the good plasticity of the soft amorphous phase, the high cohesive energy of the interface between the two phases, and the thermodynamic separation trend of the crystal phase and the amorphous phase. The dislocation cannot be formed in the fine nanocrystalline, and the thin amorphous layer between the grains can effectively resist at high temperature. The amorphous phase SiNy/Bn can effectively prevent oxygen atoms from penetrating into the coating along the grain boundary defects, which can effectively improve the oxidation resistance of the coating. Therefore, the nanocomposite coating with high hardness, good toughness, and good wear resistance can be applied to the cutting field of cutting tools with bad cutting environment, so as to give full play to its excellent mechanical and tribological properties. The specific nanocomposite structure is shown in the figure. Fig. 1. The specific nanocomposite structure. 2.4 Multilayer composite coating. Multilayer composite coating refers to a coating system formed by the superposition of two or more layers of single-layer films with different components or structures as a group of repeating units. The multilayer coatings mainly include three types: metal/metal, metal/nitride, carbide, boride, nitride, carbide, boride/nitride, carbide, boride. 11 In the same coating system, different modulation period and modulation ratio significantly affect the microstructure of the coating, and also have a greater impact on the mechanical and tribological properties of the multilayer coating. The purpose of multilayer structure modification is to coordinate the advantages of two or more kinds of thin film materials, so as to achieve the purpose of improving the overall coating performance. 12. The relevant research shows that the cracks produced by the hard brittle layer will deflect at the interface or be buffered in the soft layer, so as to effectively improve the toughness of the coating. According to Hall-Pech theory, the smaller the grain size in a certain range, the higher the hardness of the coating. According to the Kohler modulus difference strengthening theory, when the dislocation passes through the interface with different elastic modulus, the hardness mechanical properties of the coating are strengthened. Liu et al. 13 prepared W/ZrB2 nanomultilayer coatings by RF magnetron sputtering system with W and ZrB2 monolayers with similar thermal expansion coefficients. The results show that when the modulation period is 30 nanometers, the maximum hardness of the coating is 41.5 GPa, which is much higher than that of single-layer W, 19.7 GPa, and ZrB2, 32.6 GPa. On the one hand, the hardness enhancement mechanism is due to the large difference of elastic modulus between the two monolayers, and on the other hand, the thin monolayer can effectively inhibit the generation of dislocations and the growth of columnar crystals. The cross-section morphology of W/ZrB2 nanomultilayer coating is shown in the figure. IJERT 9 IS 090477 www.ijert.org. Published by International Journal of Engineering Research and Technology, IJERT. www.ijert.org. ISSN 2278-0181. Volume 9 Issue 09, September 2020. Fig. 2. The cross-section morphology of W/ZrB2 nanomultilayer coating. 2.5 High entropy alloy coating. In the 1990s, Professor Ye Junwei proposed that the alloy with 5 or more main elements with equal or close to equal atomic ratio is called high entropy alloy. Alloys, HEAS, is a new kind of material which is obtained by introducing chemical disorder into multi-principal component mixing. In order to expand the design range of alloy, the atomic fraction of each principal component is between 5%-35%. 14. Its solution strengthening and dispersion strengthening effects can greatly improve the service performance of the alloy. 15. The performance enhancement of high-entropy alloy can be attributed to four major effects. 16,17. 1. Thermodynamic effect. 2. Lattice distortion effect in structure. 3. Hysteresis diffusion effect in dynamics. 4. Cocktail effect in performance. Based on the above, new materials are developing rapidly in recent years. However, in the process of preparing high-entropy alloy bulk materials, expensive elements such as Cr, Ni, Co, W, Mo, Ti are often added, resulting in the high processing cost. 17. However, the performance of many parts depends on their surface characteristics, and the preparation of high-entropy alloy coating can obtain its excellent mechanical and tribological properties and greatly reduce the cost. The preparation of high-entropy alloy coating has been widely received general concern. Some high-entropy alloy films not only exhibit excellent properties similar to high-entropy alloys, but also superior to bulk alloys in some properties. In order to solve the problem that it is difficult to prepare the multi-element complex alloy target, the high-entropy alloy coating with the required element composition is prepared by the interaction of multiple simple alloy targets. Based on the above, high-entropy alloy coating is warmly sought after. Qiang et al. 18 deposited alchemotadazerne high-entropy alloy coating by reactive RF magnetron sputtering in AR/N2 mixed atmosphere. The results show that the hardness of the coating is as high as 40 GPa, with low residual pressure stress, 1.04 GPa, high wear resistance and thermal stability. Relevant researchers have shown that nitrogen is introduced to form hard ceramic phase during the preparation of high-entropy alloy coating, which can realize the preparation of high-hardness coating. Moreover, Li Wei et al. 19 prepared alksphaconicrity high-entropy alloy shows that the corrosion resistance of the alloy can be effectively improved by properly increasing the aluminum content in the alloy. 3. Conclusion. In the process of cutting, the coating can effectively avoid the direct contact between the tool substrate and the processing material, and play a thermal and chemical barrier effect. With the continuous innovation of coating technology, multi-layer and multi-scale coatings gradually appear in people's vision. At present, even in the high-speed and high-temperature cutting environment, coated tools can still maintain a higher cutting life. References. 1. Wangyang Lin, Li Yingji. The friction and wear properties of TIN coating on the surface of the general parts. J. Equipment Manufacturing Technology, 2017, 12-143-145. 2. Barrier, Kakar, Akia SS, ETAL wear protection potential of tin coatings for 304 stainless steels used in rotating parts during olive oil extraction. J. Surface and Coatings Technology, 2016 S0257897216306703. 3. Chenli Wang Xiaoquanyin Fei. Research on Microstructure and Mechanical Properties of Tin Coating. J. Cemented Carbide 2006, 018-10. 4. Qi Dongli, Song Jianyu, Shenlong Hai. Effect of substrate temperature on microstructure and properties of CRN coating prepared by magnetron sputtering. J. Hot Working Technology 2018-47, 18158-161. 5. Liang Jinjichen Shimen Kong Yu Shueshu Wen Zouchengui. The latest research about CRN base coating. J. Journal of Lingnan Normal University 2017 38, 0644-50. 6. Zhou Li Tao, Fan Xiangfang, Li Huilin, ETAL effect of duty ratio on surface morphology and performance of TILN coatings deposited by multi-arc ion plating. J. Materials Science and Engineering of Powder Metallurgy, 2018, 3. IJERT 9 IS 090477 www.ijert.org. Published by International Journal of Engineering Research and Technology, IJERT. www.ijert.org. ISSN, 2278-0181. Volume 9 Issue 09, September 2020. 7. Jose F., Ramaseshan R., -S, ETAL Significance of L on the Morphological and Optical Properties of TI1, XALXN Thin Films. J. Materials Chemistry and Physics, 2011, 130, 31033-1037. 8. Galindo R.E., Andrino J.L., R. Martinez, ETAL Improving the Oxidation Resistance of AL-CRN Coatings by Tailoring Chromium Out Diffusion. J. Spectrochemica Acta Part B Atomic Spectroscopy, 2010, 65, 11950-958. 9. Xaliti. Lark, Nui, Industrielle Beschichtungstechnologie. J. Werkstatt Betrieb, 2003, 136, 312-17. 10. K. Bobson T. Brigelman N. C. Krupp M. Carlet. Nanocomposite, TILCRSI, NHPPMS Coatings for High Performance Cutting Tools. J. Surface and Coatings Technology 2019, 378. 11. Ao Yankui. Preparation and high-temperature oxidation behavior of several nano-multi-component nitride coatings. D. Guangdong University of Technology. 12 Fan De, Lei Hao, Guo Qian, Gongjun, Sun Xiao. Effects of modulation period on mechanical properties of magnetron sputtered WB2/CRN multilayer films. J. Surface Technology 2017,46, 06156-160. 13 GQ Lu Y.B Kong H.Y Wang F.Y Shui X.Y Den D.J Li effect of modulation period on the structure and mechanical properties of nanoscale W/ZRB2 multilayered coatings. J. Physics Prostia 2011,18. 14 Ye JW, Chen SK, Lin SJ, ETAL nanostructured high-entropy alloys with multiple principal elements, novel alloy design concepts and outcomes. J. Advanced Engineering Materials, 2004, 6, 5299-303. 15 UNL. Microstructure and mechanical performance of ALX-CO CRC UFA-NI high-entropy alloys. J. Rare Metal Materials and Engineering, 2009, 38, 91602-1607. 16 Su Quan, Lu Jian, Huang Yanbin, Xielu, Huang Junxiang, Wang Xian Yang. Current status of research on high-entropy alloy coatings. J. Electroplating and Finishing 2019 38, 07326-333. 17 Wei Li Ping Lu Peter K. Liao. Microstructures and Properties of High-Entropy Alloy Films and Coatings, a Review. J. Materials Research Letters 2018,6, 4. 18 Keng Hao Chen Chia Han Lai Sujin Linjin Wei Ye. Structural and Mechanical Properties of Multi-Element, AL-CRMO TIZR, NX Coatings by Reactive Magnetron Sputtering. J. Thin Solid Films 2010,519, 10. 19 Li Wei, Lu Guizhong, Guo Jiang. Microstructure and Electrochemical Properties of ALX FACO NICRTI High Entropy Alloys %ALX FACO NICRTI J. Foundry, 2009, 058, 005-431-435. IJERT 9 IS 090477 www.ijert.org